So this is our second video on properties of logs. And we want to look at expanding logs. There are three properties of expanding logs. So the background information is, let's say you have a positive number a, that's not 1, and then you have three other numbers, x, which is positive, y, which is positive, and r, which can be any real number. It could be positive, negative, 0, whatever r wants to be. You got these three properties. The first property says if I take the log base a of two things multiplied together, x times y, that you can split these logs apart and say log base a of x plus log base a of y. The second property says if I take the log base a of two things divided by each other, x over y, that can split these apart as log base a of x minus the log base a of y. And the third property says that if I have this log base a of x to some power, I can take that power, basically take that power out in front and make it a coefficient of the log, something that's multiplied by the log. I guess we'll prove these. I'll do the proofs of these. So first I'll prove the first one. So the first one, let's pretend the first one is true. Let's say I have log base a of x times y. Let's pretend that's equal to the log base a of x plus the log base a of y. Okay, so that's their first property. If that is true, this is equivalent to saying, remember how this works. You start off with the logarithmic base a, and you raise that to the right-hand side of the equation. That becomes your exponent, log base a of x plus log base a of y. And then that's going to be equal to the argument inside of that log on the left-hand side. The argument is x times y. So let's see if this is true. Does this check out? Does this check out? If it checks out, then that means our property that we started with is true. Let's see. Well, I don't know if you know your properties of exponents very well, but you should. One of your properties of your exponent says if you have a to two things added together, you can break this up into a times the first thing, log base a of x, multiplied by a to the second thing, log base a of y. That's a property of exponents that hopefully you're familiar with. And then using our inverse properties of logs, we can take exponential base a and cancel out with logarithmic base a. And that's going to be simply a blue x. And then we have a times in red. And then we can take exponential base a and cancel out with logarithmic base a again. And we get the y. So we get x times y equals xy. And that's true, right? Which is true. So since this checks out, that means our original thing back here in the box is true. Okay, so that's the first property. The second property, we want to prove that one. That one says that the log base a of x divided by y is the same thing as the log base a of x minus the log base a of y. Let's check it if it's true. So if I wanted to write this in exponential form, I'd start with my logarithmic base a in red, which becomes my exponential base a. I'm going to raise that to the blue power, log base a of x minus log base a of y. And that's going to be equal to what's in the argument in green, x over y. Now let's check this out and see if it's correct. If it is, then our property is right. It means we would have proven our property. Here we go. Okay, so if you look at the subtraction symbol right here, using your properties of exponents, you can write this as a to the log base a of x divided by a to the log base a of y. That comes from your properties of exponents. Hopefully you would have learned somewhere in the past. And a more basic algebra course, and this is supposed to be x over y. Well, let's see if that's true. Well, using your inverse properties, logarithms, you can cancel exponential base a with logarithmic base a, and you get x on top. And on bottom, you cancel exponential base a with logarithmic base a, and you just get to y on bottom. So x equals y, x over y equals x over y, and that checks out, which is true. So since that's true, that means the original thing back in the box must be true. Okay, finally, the third property. We have what? Log base a of x to the r is supposed to be the same thing as r times the log base a of x. This is what we want to show is true. So to show this is true, what we're going to do, we're going to start with the exponential base a in red and raise that to the blue, r times log base a of x. And you complete the circle, you go back to the argument of the first log, and you get x to the r. Okay. Now if this thing on the right-hand side checks out to be true, then that means our original property was true. Let's see. I'm going to go back to using my properties of exponents. So one of your properties of exponents says we can rewrite this as a. So when these two things here are multiplied together in yellow, I can rewrite this as a to the log base a of x. I can put a parenthesis around here and put the r out top like that. And the question is this equal to x to the r? Let's see. Well, you can use your properties of inverse properties of logs. You can cancel the exponential base a with the logarithmic base a, and you get simply a blue x that drops down to the r power. Is that the same thing as x to the r power? Yes. So it checks out. So that means this thing back here in the box is true. Okay, so we got our inverse properties established. Let's actually use them. Let's do some exercises where we employ these properties. Okay. Exercises. Expand each logarithm and simplify. So my first problem, I have log of 1,000 times x cubed times y squared. So the idea is I want to expand this. So notice inside of our argument we have three different components. That are multiplied together, right? 1,000 times x cubed times y squared. So what we can do, we can use our very first property back here. This one here, which says you can split up things multiplied together inside of an argument into multiple logs. So I'm going to write this as the log of 1,000 plus the log of x cubed plus the log of y squared. So that's using our first property. Now remember that when you see log, this is understood to be base 10. When it doesn't have a base, it's understood to be base 10. So I'm going to write this as log base 10. Now the reason I'm writing it base 10 is because I want to be able to simplify log of 1,000. So I'm writing it as log base 10. And we know 1,000 can be rewritten as 10 to the third power, right? 10 to the third power. Now, if I continue, I go to my second log of x cubed. I can take the x cubed out front. That's using my third property. My third property, this one right here, right where I take the exponent out front. And I'm going to have 3 times log of simply x. And then I go to my third log, and I can do the same thing. I can take the square out front, right? I have 2 times log of simply y. Now I'm going to do one more thing to expand this and simplify. I'm going to cancel the log base 10 with the exponential base 10. I'll be left with simply 3 plus 3. And rather than putting the multiplication symbol, we don't have to put the multiplication symbol, it's implied. If you don't write it, log of x plus 2 log of y. There's my final answer. So that's expanded and simplified both. 3 plus 3 log of x plus 2 log of y. Okay, number 2. So same instructions, you want to expand and simplify. Let's say we have the log base 5. So this time we're given a base of 125. A to the 4th, b to the 18th. Okay, so I basically have multiple things going on. I have this blue 125 multiplied by this red a to the 4th, and then it's divided by b to the 18th. Now inside of the argument, the largest operation that's occurring is the division, you could say. I mean, you have multiplication between 125 and a to the 4th. But more importantly, you want to get rid of that division first. So I'm going to leave, I'm going to break apart this division right here. This division, what color am I going to use? I'm going to use a minus, a yellow for the division. That fraction bar is a yellow fraction bar. So we're going to leave 125 and a to the 4th together inside of one log. And we're going to turn that division there, we're going to turn that into a separation of logs where we subtract. So basically this division bar here, this fraction bar, it becomes a minus and then another log, log base 5 of your denominator. Your denominator is b to the 18th. Okay? So now what I can do, I can go to the first log, log base 5 of 125 times a to the 4th, and I can separate that. So there's multiplication, right? There's multiplication between 125 and a to the 4th. I can separate those. So I can do log base 5. And because this is multiplication between 125 and a to the 4th, I can do a plus log base 5 of. Okay, so the first argument should have 125. The second argument should have a to the 4th. We're going to put a minus sign. There's one thing I can do. I can use that third property where we take the 18 out front, and I get 18 times log base 5 of b. Come on, right. Okay, so I took the 18 out front. Okay, I want to continue simplifying. So next I'm going to look at my log base 5 of 125. I'm going to ask, can I simplify that? I can, right? If I think about 125, I can rewrite that as 5 to the 3rd power. Right, 5 to the 3rd power is 125. Okay, now I'm going to continue. If I go to my log base 5 of a to the 4th, I can take this 4th power out front, and that'll be 4 times log base 5 of a. And then we have minus 18 log base 5 of b. Okay, and I can do one more step where basically I cancel out my log base 5 with my exponential base 5, and I get for an answer 3 coming down plus 4 log base 5 of a minus 18 log base 5 of b. So that's an expansion of the log. So we start off with a single log, right, just a single log, and we expanded it. 2 logs and then a number out front of 3. So there are actually 3 different terms. 3 is the first term, 4 log base 5 of a is the second term, and minus 18 log base 5 of b is the third term. So expanded and simplified. All right, number 3. number 3. So these are a little tricky. Let's say we have the natural log of x to the 120. That should be a 120 there. Times the square root of y over e to the 45. So the big operation that's occurring here within the argument, so I'm going to call this x to the 120 blue. I'm going to call the square root of y red. And on bottom, I'm going to call e to the 45. I'm going to call that green. But the big operation here is division, and we're going to have to separate that division first. So let's separate the division. So I'm going to have, let's see, the natural log of, first of all, x to the 120, square root of y. That division there, we separate that. It becomes a minus another log, natural log of e to the 45. Okay, so now I can look at my first log, natural log of x to the 120 times the square root of y, and I can separate that. Notice there's multiplication between the x to the 120 and the square root of y, so we can separate that. Remember, multiplication separates as 2 logs added, so we're going to have 2 natural logs added. We're going to have natural log of x to the 120 plus natural log of the square root of y. Okay, minus, now remember the natural log. The natural log here is the same thing as log base e, right? I'm going to have e to the 45 power. So the log base e cancels with the exponential base e, and there on the end, I'm going to end up with a minus 45. Now if I continue in the front, on this next line, I can take this 120 out front. 120 times the natural log of x. That would be my third property, taking an exponent out front of a log. And this next one, a square root, we can rewrite a square root as y to the 1/2 power. Y to the 1/2 power. So we'll end up with, let's see, 120 natural log of x. Plus, here we go, we're going to take this 1/2 power out front. We're going to have 1/2 times natural log of y, and then minus 45. So in conclusion, our final answer is 120 natural log of x plus 1/2 natural log of y minus 45. That's expanded and simplified entirely. Okay, I guess we'll do one more. So these are actually involved, a bit involved. There's a lot going on with these. This is the last one. This will be the most difficult one. Natural log of the cube root of a whole bunch of stuff. X squared e to the 9 times y over z to the 30 power. Wow, this is a lot going on here. So first of all, I have the natural log. I'm going to rewrite that. Now, the biggest thing happening overall is this. So let's write things down. So we have we have a x squared here, and I'll call that blue. We have e to the 9y. I'll call that red. We have a z to the 30. I'm going to call that z to the 30. I'll call green. But something else that's happening overall, over everything, is this big old cube root. I'm going to make that a violet color. So remember a cube root. That's the same thing as writing the 1/3 power. So we're going to write everything x squared e to the 9y over z to the 30 power. And we're going to put a big old purple parentheses around all of this here inside the argument. So this cube root, the 3 goes on bottom as the fractional exponent, and it's understood to all of this be raised to the 1 power here, so I'll put a 1 on top. So the cube root is the same thing as the 1/3 power. Now notice that this 1/3 power is around the entire argument. It's around the entire argument. So what we're going to do, we're going to take this 1/3 power, we're going to bring it out front. So you can do that so long as it's around the entire argument. So we're going to take a 1/3 and bring it out front. So we're going to have 1/3 times the natural log of x squared times e to the 9y divided by z to the 30. So we got rid of that big old cube root. We turned it into a 1/3 power and brought it out front since it was an exponent over the entire argument. Because the next thing I'm going to do, I'm going to write down 1/3 natural log. I'm going to deal with this this division here. That's the next big thing. We have to get rid of the division inside of this log. So we're going to break this up into, okay, so actually, let's write this 1/3 out front. So 1/3 is multiplied by the entire log. 1/3 is multiplied by the entire log. Do you have to write this bracket or parentheses? I'm going to call it bracket. I have to write this bracket out front because 1/3 is being multiplied by the entire log, and we're going to break this log up into parts. So put a bracket there. 1/3 times this entire log. So this log is going to break up into two parts based on this division here inside of the argument. So we're going to have the top, the natural log of the top, x squared, e to the 9y, and the division there becomes a minus sign when it breaks up into two logs. And then you have the natural log of z to the 30 power. Okay? So I'm going to have, let's see, 1/3. I'm going to put a bracket. So now inside of the first log, where you have the argument x squared e to the 9y, we can break that up into two because there's multiplication, right? You have natural log of x squared plus the natural log of e to the 9y and subtract the natural log of, well, hold up a second. We can actually take this 30 out front right now. Take that out in front. So let's go back and take that out in front. So we have a minus. Where's my minus sign? Minus, so I'm taking that 30 out front, 30 times the natural log of z. Okay. So I simplified, and I want to keep simplifying. Let's continue. We have this 1/3 out front, multiplied by this entire logarithmic expression. So in this first log, natural log of x squared, we can take the exponent of the argument out front. It's 2 times the natural log of x. And then this, remember, natural log is the same thing as log base e. We're going to rewrite that because we have an exponential base, e to the 9y. And then here we have, it looks like minus 30 natural log of z. So for my next step, I can basically cancel out the log base e and the exponential base e. So for my next step, I'll write 1/3 out front, big old bracket, 2 natural log of x, plus, so we said log base e canceled with an exponential base e, and we have a 9y that drops down, minus 30 natural log of z. So my final step here is to distribute this 1/3 through. I'm going to multiply 1/3 through. I'm going to multiply 1/3 times 2. What's 1/3 times 2? Well, 1/3 times 2, 2 over 1, is what? 1 times 2, 2. 3 times 1, 3. 2/3. So I'm going to have 2/3 natural log of x plus, okay, so then I'm going to take 1/3 times 9y. What's 1/3 times 9y? Well, 1/3 times 9 over 1 is 1 times 9 is 9, 3 times 1 is 3, 9 over 3 is 3. So we're going to have 3y. And then minus, let's see, what's 1/3 times 30 natural log of z? Well, let's take 1/3 times 30. 1/3 times 30 over 1. You multiply the top with the top, you get 30. The bottom with the bottom, 3 times 1 is 3, and 30 divided by 3 is 10. So 10 natural log of z.